So, hello friends, hope you are doing well. In our next session, I just want to focus on the designing of the utility scale solar power plant. In the past sessions, I have also tried to cover the system which is used in the standalone mode or a grid-tied system also. But in the case of grid-tied system, the magnitude of the rooftop applications are usually 1 kilowatt to 1.5 kilowatt or sometimes 2 kilowatt. But in this case, if we are considering the solar power plant designing for utility scale, it might be a 1 megawatt to 5 megawatt or sometimes more than that. Usually people are designing this kind of power plant in the open space area like desert, or you can say the rooftop of large parking or roof of large institutions or government organizations where the sufficient space is available in the terrace for large building. So now we need to design this solar power plant. If you can start the designing of the solar power plant, we are considering the various aspects of that. The first aspect is the sizing of the plant. Means how we can size the plant. So, if you can start with the solar power plant general layout, we are having a number of panels that is to be connected in series and parallel configuration that could be matched with the inverter voltage and current, and this DC power is converting into 3-phase AC power with the suitable amount of protection devices like MCCB or other protection devices. The solar meter is connected to get the data of exported power into the meter. So it is also known as export meter or solar meter, and this is the main transformer, and through this main transformer it is connected with the grid. This is the normal, or you can say generalized layout of solar power plant. But in the specific case, particularly say for example nearby our campus, we are having the multiple transformer. We have installations of 1 megawatt. In the 1 megawatt installations, we are having 4 inverters of each 250 kVA, which is connected with 250 kVA main transformer, and those transformers are connected with the common transformer of 1250 kVA, and then it is connected with the grid. So depending upon the plant to plant, the configuration may be changed, but this is what the generalized layout of the solar power plant. Talking about the dominating technology and its advancement, this is one of the nice technology known as the BIPV, that is Building Integrated Photovoltaics. We are having 3 types of solar cells. One is of monocrystalline, second is of polycrystalline, and third one is of thin film. These cells are accommodated, and we can have one photovoltaic panels or a panel that is to be used in the solar power plants. This is a new concept of the flexible solar panel. Many of you might heard that. It is also in the form of stickers, where we can have a stickers of solar panel on the flexible shape. And in market there are number of color varieties are also available. But usually Indian weather is good for the polycrystalline material. And in the previous sessions we have also discussed about the orientation of the panel. That is, panel is oriented towards south because we are in the northern hemisphere. So ultimately the polycrystalline panels generally installed oriented towards south at an angle of latitude. So with this we will start with the design. If you are considering the full cell panel of 320 watt, these are the temperature, coefficient of power, voltage and current. This is degradation in the power minus 0.40% per degree centigrade. Similarly, voltage and current. Obviously, the current will rise in this case because it is usually the temperature is creating the dominating effect for the voltage and the radiation creating the dominating effect for the current. Talking about the particular cell, so if we are considering the standard test condition, we are having 1000 watt per meter square radiation and 25 degree centigrade temperature. So in this case, if we are considering 25 degree centigrade temperature, over here we are considering the power drop due to rise in temperature. And if you can start with the same thing, we'll start with the power drop of 345. That is what the peak power rating of the solar panel in this case. And these are the voltage drop and current rise with the increment in temperature. So in this case, this is the change in cell temperature delta, and accordingly how much change in the voltage drop and current rise would be there for the typical solar panel of 320 watt each. And this is also the change in delta. I mean, small change in temperature creates the huge impact in the radiation. If we are considering the GTI, that is grid tied inverter technology. So this is one of the Sunny Central inverter, which is of SMA, one of the leading inverter company. It is also known as the Sunny Central inverter of 2.2 MVA or 2200 kVA with its data sheet. You may download this data sheet from the internet, or you may pause the video and check the data. This is one of the other manufacturing unit of SMA string inverter, 75 kVA, Sunny high power peak 1, which can withstand up to 1000 volt. Now in the current situation, the solar panel might be connected in the series formation, because if you will add the panel in series, at that time the voltage will rise. It can withstand up to 1500 volt. So this is the technology. In the case of the string inverter, it can be withstand up to 1000 volt. During the experiment in the laboratory, we have also seen this thing. The maximum withstand voltage is 1000 volt. That has been clearly mentioned on the back side of the panel as a small data sheet available, or pasted it on the back side of the panel. One more inverter for small scale application, the Sunny Boy, which can withstand up to 600 volt. In the solar power plant of ours nearby our institute, we are having such 5 kVA Sunny Boy inverters are installed for particularly the oriented maximum power point trackers power plant. It means that we are having a physical tracking mechanism known as the mechanical tracker, and they have connected with such kind of Sunny Boy type of inverter, which is basically a manufacturer of SMA or manufactured by SMA. This is what the simple concept of the net and gross metering. In the case of gross metering, we are having the two meters, import meter and the export meter. In the case of net metering, we are having the bidirectional metering circuit. If we can talk about the Ahmedabad or Gandhinagar, where we are considering the torrent meters, it is a actual bidirectional meter. So it can have a data. That's what the power consumed by any house or utility, house from the utility or the grid, or we can also have an export meter, so we can feed the power through the panels. This can be done using single meter. So let's have a revise the same thing. That's what we revised in the past sessions. These are the thumb rules for the losses calculation. They are: the PV panel losses are 3%, inverter losses are 3%. If you remember our earlier session of the designing of standalone system, in that case we assume the efficiency of the inverter in between 90% to 97%. In that case, the losses are of 3%. We are having the AC losses of 5%, mismatching of the losses because it is varying depending upon the climatic condition. We can have to match the impedance also. It is 3%. soiling losses, most important, is 5%, and the temperature losses we have considered in the earlier slide. So we want to connect a PV array which will provide the desired power despite of all the losses. So let's design the solar power plant. If you want to design the solar power plant, we shall consider the bill of the client. So if you can check the electricity bill of the client, you have to check the load and energy consumption. So for example, let's take total consumption for a day is 3000 kilowatt hour. So now to identify the requirement amount of DC power for solar power plant capacity, we will take our conventional example of 1 kilowatt of power. That is 1 kilowatt peak power of solar PV can give us 4 to 5 units in a day. In this case, we have also assumed 4.5 hours for daily sunshine. So if we can convert this into DC power, that is the energy for 1 kilowatt, and we are considering 4 kilowatt hour. I am considering 4 over here, that is 4 units per day. So 3000 kilowatt is the consumption for a day. For 1 kilowatt we are considering, divide by 4 kilowatt hour, that is 750 kilowatt peak. So ideally we required 750 kilowatt peak solar power plant to have 3000 units generations every day. Now if we can go back, we need to consider some losses over here. This losses, so we can have a losses, and we are converting into per unit. So 750 kilowatt divided by 1 minus, these are the losses, divided by 100. Over here we are considering the losses of the module at 75 degree centigrade. At 75 degree centigrade we are considering the losses. So this value has been taken and it is 20 kilowatt. So if we are considering the same thing, we will get the idea of 1.229 kilowatt, that is nothing but 1.2 megawatt peak power plant. Again, I just want to note one thing. This 1.2 megawatt power plant or 1.2 megawatt power will be generating at STC. So anyhow, this 0.229, that's what we are considering are the losses, or you can say we need to maintain the ideal condition that is not possible in day-to-day life. So now we want to have this power plant. Again, in the same case, you need to design the same thing. At that time we are having 1.229 megawatt solar power plant, so we must have 10 times more area which is free from shadow. Otherwise we need to go for the shading analysis. If you are providing this much area, then we'll start with our step 1. So we need to select the best suitable technology from the previous slides. So we have selected REC twin peak, which is a nominal power of 345 watt. It has a nominal power voltage VM or VMPP of 38.7 volt. Nominal current 8.92 ampere. It has an open circuit voltage of 46.5 volt. Short circuit current of 9.36 ampere. The module efficiency is 17.2. So the ultimate case is usually depending upon the VOC and VM. So those who are working with the VOC and VM, ultimately your VM is 1.2 times less than the VOC. That has been also considered in the same case over here. So number of modules that is to be required for this 1.229 megawatt or 1229 kilowatt peak divided by this should be converting into kilowatt. That is, this much modules are required to generate this much amount of power. So now what we try to do is, we have this much capacity and this much area. Now we will select the suitable size of the inverter and string. If we can select the 75 kVA of SMA inverter with the maximum voltage of 1000, we can design our string in such a way that the string must have the voltage at least at 1000 or less than that. So we can calculate VOC for the module is 46.5 volt. So number of panels to be connected in string is 1000 divided by 46.5, that is 21 panels. So VDC for 21 panels is for 21 panels, 46.5 into 21, that is 976.5, and the power rating is 7.245 kilowatt per string. So we are having a string which is of 21 panels which are generating around 1000 volt and which has a power rating of 7.2 kilowatt. So again this thing remains same, and in step 3 we will go for the sizing of inverter. So we can oversize the inverter by keeping the voltages of AC and DC, because AC and DC voltages are not same. So we are oversizing the inverter by keeping a constant of 1.4, and we are multiplying this 1.4 if we are taking this 60 kilowatt inverter. So we are having the 84 kilowatt peak, that is a DC power fed to the inverter. Now to calculate the how many string for 21 panels of 345 watt peak or 7.245 will be accommodated in the single inverter. So we are having the 84 divided by 7.245, considering the 84 kilowatt peak power, we are having 12 number of strings that could be processed in the same inverter. So if you can go back over here, we are considering the 12 strings that could be accommodated with one inverter. That's what we designed, and that rating of the inverter is 60 kilowatt, and accordingly we are going to design the same thing. So if we can go with the 84 kilowatt peak power divided by 7.245, it is 12. Such 21 panels into the same power rating, we are having the same output. For 12 strings, we are multiplying this 12 with this, so we are getting 86.94 kilowatt. Similarly, we can take one more case. If you can take 22 panels, each of the same capacity, we need only 11 strings. So this is what the change in the power. If you go for the 12 strings or 11 strings, it is depending upon the user. So this grid tied inverter of the Sunny Tri-Power Core 1, again the manufacturer is SMA, and we are considering this maximum output current also, because till this discussion we have considered the values of the voltage. So this is the maximum current that could be withstood by the inverter, as it is taking DC power from the panel. We are considering the maximum output current and rated almost similar, because this is the shortest transmission from the panel to the inverter. As I mentioned that the 1500 volt is accommodated over here, so it can withstand up to 1500 volt also. Then accordingly this design will be changed. So now we will again go for the one more concept of 50 kVA inverter. By considering the oversizing of 1.5, then we are having the 75 kilowatt peak, that is DC power fed to the inverter. So if we are using the features of multiple MPPT in the inverter, we can oversize the matrix differently. Suppose I will take 22 panels, 345 watt peak each. So one string will give us 7.5 kilowatt peak. Such 8 strings, it will give us the 60 kilowatt. So I'll get the power. I'll also go for the 20 panels of 345 watt peak. So I'll get the 7.245 kilowatt peak. If I'll go for 2 strings, I'll get 14.490 kilowatt peak. So 2 into this, If you can add this two, you will get 75.21 kilowatt peak. So for number of required solar modules divided by inverter, if you do, you will get from this 176 modules plus 40 modules, that is 216 number of modules that is to be connected with the single inverter. So now this is for one inverter. So how much inverters will require? So we require the number of inverters is 1.229, it is megawatt power. If you are converting into kilowatt power, it is 1.229. It is 1.229. So number of modules are 16 into 216, that is 16 inverter and 216 panels by single inverter. So we are having the number of required modules that is matched with 3, 4, 5, 6 number. Now our plant capacity will be 16, that is number of inverters into this peak power. It is now 1192.32 kilowatt power. Now we will talk about the selection of the MCCB for all the inverters. So the 72.5 ampere highlighted with the red color is taken from the sheet of the inverter, and we are considering this 90.625 ampere, that is almost the 100 ampere. For creating the 11 kV transmission line, because it is the transmission voltage nearby the plant, considering 25 kiloampere will be the suitable fault current, we are having the delta configured solar GTI, that is grid tied inverter. So we require 3 pole MCCB, and the number of inverters equals to number of MCCB, that is 16, each of almost 100 ampere capacity. It has a 3 poles because it's a 3-phase delta connected network, 25 kiloampere withstand capacity. So we also required 16 MCCB, that is nothing but the number of inverters. So if we can talk about the selection of the main MCCB to our main distribution box, ACDB, AC distribution box, then our MCB is of typical rating of 1280, that is the breaker trip rating in amperes, to 1250 AF, that is ampere rating of the breaker frame. This means that the breaker is operated for a maximum current of, considering the overload capacity, 1500 ampere, and it is currently set to trip for all the open contacts up to 1100 amperes. So similarly we can select the higher capacity because we are still 150 amperes, that is to be there in our hand. So in step 7 we are considering the selection of the appropriate transformer, which is of 1250 kVA step up transformer. It will step up over 400 volt by 11 kilovolt, that is oil natural and natural cooling type. So with this the same thing, we are designed the transformer, and accordingly we can go further. Now this 1250 kVA transformer, that is 1.25 MVA, is available in the market. Now if you can talk about the selection of AC and DC and earthing cable. So this table shows the layout of the various cables. So first we need to draw the layout, or you can say a single line diagram. Then we'll go with the interconnection of the module depending upon the capacity. We are having the cable lengths and the most important thing, diameter, standard wire gauge diameter, SWG, for single core cable. Similarly we have one more cable to inverter to AC distribution box. These are the 4 core and 5 core and 3 core cables are used, and the earthing cable. So now if you can have a detailed layout, simple layout in the detailed manner in your mind. So ultimately we are having the solar PV. So now it is the 1 megawatt capacity. So we are having the interconnection of the multiple modules. In the multiple modules we are having the 9 ampere single core cable, because the short circuit current of the multiple modules remains same, but it is more for the single module. So as it is connected in series, it remains same. For star and delta connector, we are having the 18 ampere. Then we are having the inverter. So we are cabling this by having the interconnection from interconnection point to T or Y connector. We are connecting those cables with the inverter, and then inverter output of the inverter through cables, because we are discussing the cable section, to ACDB, means AC distribution box. Then it is connected to the transformer, and then it is connected from transformer to the grid. And we are having the DC earthing cable, which is of 6 mm square, single core, and the maximum cable length is 100 meter. So in the generation of solar PV power plant, it is depending upon overall parameters also, that is depending upon the site. The site to site this could be vary. These are aging, quality of the component, quality of the installations, irradiation behavior, because it is not the same. In which climatic zone we are going to plant this plant. The most important factor, frequency of the cleaning. Then the temperature behavior, because this behavior will be decided our voltage. Then spectrum of reception of the cell, incline and alignment, a shading if it is there, and the soiling of the modules, means on which type of soil you are going to install this module. So thanks for being calm and patient hearing for the same. So now we shall discuss the same thing in the workbook style. So I'll get the basic idea of the solar power plant calculation using step-by-step method, because in this session what is covered is the designing aspect by considering the number of possibilities or permutations and combination of the panel. In this layout we are trying to manage the same thing in the straightforward way. The first case, now we have taken the industry from the daily consumption of 3000 unit. So my DC power is 3000 into 1 kilowatt, because we are considering 1 kilowatt as a base, divide by 4 kilowatt hours, so 4 units per day, that is 750 kilowatt. Now after considering the 75 degrees centigrade cell temperature, our power will be the peak power, that is what we have required. Now we need to select the best suitable technology. So we have taken this REC twin peak module. It is the same thing that is covered in the last PPT, but that is without any kind of assumption, means it is the finalized design of the industry, this industry. Now 1229 kilowatt divided by this kilowatt, I will take the module. In step 2 we are having the selection of the inverter. So we have selected this 75 kV SMA inverter with the maximum voltage of 1000 volt. So we can design our string in such a way that our VOC of the string must be less than the 1000 volt DC. Now number of panel can be placed in the string is 1000 by our voltage, so it is 21 panels. Similarly, this 7.245 kilowatt per string, because the VDC of the panel we can take for 21 panels, it is 976.5, and then I will multiply with the current, I will get the power. So in step 3, the sizing of the inverter with the multiple MPPT of 50 kVA of the SMA by oversizing with 1.5 times, we are getting 75 kilowatt peak, that is DC power fed to the inverter for 22 panels for 7.590 by considering 345 watt peak, such 8 strings. So I will multiply 8 with 7.590, I will get 60.720. That is to be added with another 20 panels of 345 watt peak, get 7.245, and such 2 strings are there. So we will get the same peak power, and then we will add the same thing. So number of modules are 176 plus 42, that is this divided by the panel rating and this divided by the panel rating. I'm sorry, over here it must be the 7.245. So if you can multiply this 20 with 345, it is over here. It might be, I'm sorry for this, 6900 peak. If we go with the 6900 peak and then we will add the same thing, we'll get the same output. Now for the number of required solar modules, it is this power divided by the module rating plus this power divided by the module rating. It is 218. Now we want this much power. We are having the shadow free area 10 times more, so in the converting this into square meter. So what we are having, number of required inverters, this divided by the power. That is what we computed in step 3. So we required 17 inverters or 16 inverters in this case, considering less than 0.5. So 16 into 216 panels, or you can say 218 panels depending upon the capacity of the inverter. We are having this much number. So the plant capacity will be 1192.32 kilowatt peak or 1.19 megawatt peak. Considering the MCCB, this I have taken again from the inverter sheet into 1.25. That is considering the higher range. It is approximately 91. We are considering this as approximated as 100 ampere. Again the number of inverters are 16 numbers, 100 ampere, 3 pole, 25 kilo ampere, MCCB equals to number of MCCB also, because each inverter has one MCCB. Now the selection of the main circuit breaker at ACDB, that is AC distribution box. So we are having this capacity and we are considering this 1500 ampere and is currently set to trip at 1100 ampere. So with this we are going to select 1250 kVA capacity of step up transformer of 400 volt, 11 kV means primary 400 volt, secondary 11 kV, oil natural and natural. In the initial part of this session I tried to talk about the 1 megawatt power plant here by our institute. So over here we are having the final transformer of 1250. So the thing is like that, we are having a 4-string inverter, each string of 250 kilowatt each. Each string inverter is 250 kVA. If you can oversize accordingly, the suppose 1.4 times you can oversize, so it could be a 325 or 350 kVA. It is connected with the individual transformer of the same capacity, but the main transformer is 1250 kVA. We have 2 poles. One, it is in our premises, that could be have a meter which can read the data of the power that is to be fed into the grid, and second, which is the authority under the SoT. In Gujarat we have a SoT. So we can make and break the connection by considering the bidirectional flow of the power in solar power plant. So with this I am going to conclude the solar power plant design section. Thank you for your patience hearing. Thank you very much.